Hello and welcome to week 2, lecture 2 of CO 442642 graph theory. Today we'll be talking about a formal proof of Brooks theorem. To remind you, we discussed the informal proof of Brooks theorem last lecture. Brooks theorem, the theorem from 1941 by Brooks, says that if G is connected, then chi of G is at most delta of G, that's the maximum degree of G, if and only if G is neither a complete graph nor an odd cycle, these two exceptional cases. And last time we outlined an informal proof sketch using the greedy coloring approach, which also works for giving a delta plus 1 coloring. And today we'll convert that into a formal written proof. So let me remind you of the proof sketch from last lecture. First, we did a couple of reductions. The first reduction we did was if G had a cut vertex V, it separates the graph into two smaller graphs, G1 and G2. We permuted the colorings on G1 and G2 that we get by minimality to agree on V to get a contradiction. But there was a technicality here that I left as an exercise for this lecture, which is why are G1 and G2 not exceptional, namely a complete graph or an odd cycle. So we'll get to that answer when we get to doing the formal written proof of that part of the proof. But for now, we'll move on to the second reduction we used, which was what if then G had a 2-cut, so a bit harder reduction, and that 2-cut being U and V. Again, we get two smaller graphs, G1 and G2, but here it was tough to know how to get it to permute the colorings to agree on U and V, and the secret was to add the edge UV, and that will force them, U and V, to get different colors in both colorings. And then we can permute the colorings to agree on both U and V. This, however, led to two new technicalities. One, why are the max degree of these two graphs when you add the edge smaller than the degree of the maximum degree of G? The other technicality being, again, why are these new graphs not exceptional, complete graphs or odd cycles? So we'll again answer both of those technical questions when we get to that part of the proof, but then we finished with greedy. So the greedy coloring approach, and the key was we picked a vertex V, and we said if the degree of V is at most delta minus 1, we could just take the reverse of a depth-first search tree ordering with root V and use greedy. So that works because then all but V certainly see only at most delta minus 1 neighbors and will be able to color, and then V only has delta minus 1 earlier neighbors, and so then also colors. In the case when delta, the degree of V was equal to delta, we had to find non-adjacent neighbors x and y of V. We could do this because they're not complete. We put them first in the ordering, colored them the same, which we are allowed to do as we're allowed to choose the colors in the beginning at least. And then we reversed a depth-first search tree ordering of G minus xy with root V and used greedy, and that works because then V actually sees at most delta minus 1 colors, even though it has delta earlier neighbors in the ordering. And that works because at that point we're 3 connected, so we can find such an order. But we'll again go through that, but now on to making this into a formal proof. So this again is an exercise in taking an informal proof sketch, where last lecture we outlined the ideas and how you come up with this proof into a more formal written proof for your development as a mathematician. So let me maybe first say that we can use a proposition. So I'll just codify this reversing a depth-first search tree ordering with an ordering proposition. So if G is a connected graph on n vertices and I give you a vertex V, then you can get an ordering V1 up to Vn, where that last vertex Vn is V, and such that every vertex has at least, that should be n of Vi, at least one neighbor later in the ordering for all I in n minus 1. So this just, proof is reverse a depth-first search tree ordering from root V, or more formally you could do this. We proceed by induction. If it's 1, it's obvious. If it's 2, then you take the components when you delete V, and as you're connected, then V has a neighbor U1 up to Uk in each of those components, and then for each of those you apply induction to Gi and Ui, get an ordering from them as prescribed by this proposition, and then concatenate all the orderings, put V at the end, and that's the desired ordering. So you can do it more formally, but the reversing a depth-first search tree is maybe the easier, more straightforward way to see that. All right, let us then move on to the proof outline. So here was a proof outline of our proof sketch. So again, it's maybe better to think from a top-down approach of how to convert this instead of just rambling into writing. So it's good to be organized when we're doing the writing. So here's an outline of a proof of Brooks' theorem. We say suppose not, we have a beginning, so that tells us we're going to go by contradiction. We let G be a counterexample with V of G minimized. And if delta of G is at most 2, the result is standard. So I could include this part in the proof, as you'll see, but instead we'll just skip the odd cycle case, as that's from undergrad graph theory and rather standard. So we assume that delta of G is greater than or equal to 3. So then we do our two claims. Claim 1, there does not exist a cut vertex of G, and we'll give a proof for that in a little bit. And then claim 2, which we'll also have a proof for, there does not exist a 2-cut of G, and then the finish that we just described, which we'll write up a little more formally. So that is our outline, and now we'll move on to the proof of claim 1. Claim 1, there does not exist a cut vertex of G, so proof, again, let's start with suppose not, we'll go by contradiction here as well. So that is, so we could just say what that is, there exists a cut vertex V of G, and more formally there's then two connected subgraphs G1, G2 of G, such that G1 cap G2 is equal to V, so they only intersect in this vertex V, and G1 union G2 is the whole graph G, and of course then they're both smaller in the number of vertices. And as G1 and G2 are subgraphs of G, we have that rather easily that the maximum degree of Gi is at most maximum degree of G for each I in 1 and 2. And then we got to this technicality we described. Why are G1 and G2 not the complete graphs? And here we don't have to worry about odd cycles anymore because we're dealing with delta greater than or equal to 3, but we have to worry about them being complete. So why are they not complete? Well, here's the answer. Moreover, as G is connected, we would say, we have for each I in 1, 2, that the degree Gi of V is at least 1. So if you're connected, then the cut vertex has to have a neighbor into both subgraphs, G1 and G2, but that means that in both subgraphs it has degree at most delta of G minus 1. And that then implies, of course, that it cannot, hence Gi is not equal to K delta of G plus 1, since that has every vertex having degree delta. And that establishes that, and thus by the minimality of G, there exists delta of G colorings phi I of Gi for each I in 1, 2. And then by permuting the colors of phi2 as necessary, we can assume without loss of generality that phi1 of V is equal to phi2 of D. So we get them to agree on V, but then phi1 union phi2, if we just take the colorings together at that point, it is a delta G coloring of G, a contradiction. Okay, so we have established this proof of claim 1. What about claim 2? There does not exist a 2-cut of G. Same idea, suppose not. And again, we say what that is. So that is, there exists a 2-cut. So here instead of UV, maybe it's mildly more convenient to use V1 and V2 to make the statements write a little easier. So we have V1, V2 of G and two connected subgraphs, again G1, G2 of G, so we're doing this labeling, such that G1 cap G2 is now V1, V2, and G1 union G2 is G, and they're both smaller. The technicality, so we had two, but we'll just deal with the first. Why are the max degrees of these new graphs, when you add, that should be V1 and V2, at most delta of G? So why? Well, as G is connected and G does not have a cut vertex by claim 1, we have for all I, j, and 1, 2, that degree Gi of Vj is at least 1, right? So again, if you don't have a cut vertex and you're connected, then each of these vertices in the middle must have a neighbor into both sides. And that hence implies that they have degree on either side at most delta minus 1. And thus when we add the edge V1, V2, we get maximum degree at most delta. So that handles that technicality. What about the other one? Why are these new graphs not equal to the complete graph, K delta of G plus 1? Well, that's a good question. And actually the answer is one could be. So even in the delta greater than or equal to 3 case, we can prevent one of them, but not both maybe. So maybe one of them could actually be. This is a problem. This is a technicality. And as I hinted last time, there's a fix for this. How do we fix this? So how do we fix this problem that one of them could be complete? So maybe if you haven't thought about it, again, if you want to pause and think about this one, but the fix is a little hard. The answer is we choose V1 and V2 more optimally. We get to choose actually a 2-cut, so maybe we can find a more optimal 2-cut that avoids this. So let's go ahead and do that. We choose v1, v2, g1, g2, such that neither g1 plus v1, v2 nor g2 plus v1, v2 is equal to this exceptional case, if possible. So we add in that line when we do the choosing, and then I can go ahead and complete the rest of the proof, explaining to you how to actually make sure we're in this case. So let me do that on a different slide. So now we've done all that, we check the maximum degree, and now we handle this technicality. Next, suppose that there exists an I in 1, 2, such that gi plus v1, v2 is this complete graph. Without loss of generality, we assume that I is 1. Doesn't make a difference. Let's just say it's 1. And so now what do? We let v1 prime be the neighbor of v1 in g2 minus v2. Because if you think about it, it has at least one neighbor, because of the connected no cut vertex argument we made a little bit ago, but actually only has one then. So it only has one such neighbor. Why? Well, I have to have at least degree delta in that k delta of g plus 1. Now you delete v1, v2, so it has delta minus 1, so it only has 1 left over for g2 minus v2. So then what do? Well, we found a new vertex v1 prime. We let g1 prime be g1 plus the edge v1, v1 prime, and g2 prime be g2 minus v1. So we shift the 2 cut from being on v1, v2 to being on v1 prime, v2. And now you can just argue that that is a better cut, that it has neither side being exceptional, the complete graph. Why? Because look at the degree in g2 prime of v1 prime. Well, it only had one neighbor into the other side, namely v1, so it'd have to have at least 2 because delta is greater than or equal to 3. And so now, what about the degree g1 prime? Well, then v2 would have to have at least 2 neighbors back into g1 prime, and we find that gi prime plus this edge does not equal k delta of g plus 1 for each I in 2. But then v1 prime, v2, and g1 prime, g2 contradict this choice of v1, v2, g1, g2. And so then that concludes the exceptional case, and then we say, so we assume that you add the edges, they don't get k delta of g plus 1, and thus by the minimality of g, there exists delta of g colorings, phi of gi, for each I in 1, 2. And by permuting the colors of phi2 as necessary, again, we can assume that phi1 of vj is equal to phi2 of vj for each j and 2, so you can get them to agree on these, and then phi1 union phi2 is a delta g coloring of g, a contradiction. So now on to the finish. So this is rather easy. We just say by claims 1 and 2, we have that G is 3 connected. You let V be in V of G. We handle the case again where degree of G of V is equal to delta of G minus 1. By this ordering proposition, you get this nice ordering. Again, that should be VI. You get N of VI gets you a neighbor always later, so you can greedily color in that order, and that yields a delta of G coloring of G, a contradiction. So in the other case, we assume that degree G of V is delta of G, and since G is not complete, there exists distinct X and Y in the neighborhood of V that are non-adjacent, as we had mentioned. And then as G is 3 connected, we find that G minus XY is connected. And so again, by this ordering proposition, we get a nice ordering. And now we color, this time of G minus XY, we color X and Y with color 1, say. Not importantly the same, then we greedily color in that order. And this yields a coloring, a delta G coloring of G, a contradiction. And we could spell out more how the greedily coloring works in each of these cases, but if you take it to mean assign the lowest possible number and 1 up to delta of G that isn't already used by its earlier neighbors, then it would be well defined what all of that would be, and it would be easy to just go ahead and check that that would work. But we've covered the important technical parts of the proof with this proof and handled all the various technicalities that arose. So that concludes this lecture for today, and next time we'll pick up with going beyond Brooks' theorem, what other theorems are known to be true. Thank you.